Okay, welcome back everybody. So in the last video, I kind of previewed that what I wanted to talk about in this video, and that's indefinite integrals. And so again, we looked at these functions like x squared plus 3 and x squared plus 1. We took their derivative and got 2x. And then we asked like what would an antiderivative look like? Well, really, these are the antiderivatives. They're examples of antiderivatives. The things in this column here. And then the indefinite integral is like the whole family of antiderivatives. And what I mean by that is it's just all the things that if I were to take the derivative of it, I would get 2x. And so we said in the last video that those things would be, let me get the right color here. Those things would be x squared plus the constant of integration c. So this is what's known as the indefinite integral of the function 2x. So then if we look at these functions in pink, we have x to the fifth plus 2x and x to the fifth plus 2x plus 7. And we know that if you take the derivative of either one of those functions, you're going to get 5x to the fourth plus 2. And so we can take the integral and get x to the fifth plus 2x plus c, constant of integration. And I should note that this notation here, this indefinite integral notation, is a little different than a lot of notations you've seen before because it's representing like a function that eats other functions, but it has this big squiggly s at the beginning, and it has the dx at the end. And what that means is that it's telling you to take the indefinite integral of whatever is inside the parentheses with respect to x. So that dx there is saying take the integral with respect to the variable x. It's like the differential that we saw earlier in this course. And so the important thing here is like this whole thing, the s, the brackets, and the dx, that's the notation for the function. And then whatever goes inside here is what we're taking the integral of. So think of this as I'm taking 5x to the fourth plus 2 and sticking it inside between the s and the dx. Okay, so there's the definition. It says, given a function f, the indefinite integral of f is denoted by, again, the squiggly s, this long s, which is going to stand for sum. And then you plug the f of x in the middle, and then the dx is the end, okay? That's the most general antiderivative of f. So it's the big function f, or it's any, if you were to take any antiderivative of little f, call it big F, then we add the constant of integration plus c. Okay, so f of x is called the integrand. The integrand is the thing that sits inside of the s and the dx. The variable x is the variable of integration because we're taking the integral with respect to x there. So that dx is saying that's like a differential of x. That's the variable of integration. So now let's see here. I'm sorry, I need to fix my functions here because I wanted to give you a bunch of functions in t now. So f of t could be t cubed, or sine of t, or secant squared t, or even t to the fifth plus 7. And now I want to take the integral of f of t with respect to t. Okay, so that's, notice that I've changed the variable of integration to t here. That's why we use this notation, I guess. And now you guys should be able to do this. What's t to the third? What's the integral of that? Well, the derivative you would be subtracting 1 from the exponent and bringing it out front, right? Now what we're going to do is we're going to add 1 to the exponent, and then we're going to divide. And then we're going to add c. And then you could always check by taking the derivative again. If you take the derivative, you get 4t cubed over 4 plus 0. And that simplifies down to t cubed. So we got back to where we started there. Perfect. Okay, what about sine of t? Well, remember I told you to draw that little circle and go counterclockwise. So usually the derivative of sine of t is cosine of t, but the antiderivative of the integral is going to be negative cosine of t. So this is negative cosine of t plus c. And then secant squared t. Well, what can you take the derivative of to get secant squared t? I think if you've memorized the table, you'd say, oh, it's just tangent of t. Okay, so hopefully you know that already, that if I take the derivative of tangent of t, you get secant squared t. If not, go back and review your trig derivatives because we're just going to go in the opposite direction now. Okay, and then what about t to the fifth plus 7? Well, that's just a polynomial, so that's the easy rule. We just take t to the sixth divided by 6 plus 7t, right? Because you can think of that 7 as 7t to the 0, and then you follow the rule, you get t to the 1 divided by 1, so you get 7t. And then you got to always remember the constant of integration, okay? Okay, so hopefully this is starting to make sense. We're just undoing the derivative, but when we do that, we have to add this constant of integration. And integrals have kind of funky notation, but once you get used to it, you can parse it. You say, okay, this is the integral of this f of t, which is the integrand, with respect to t. So that dt is saying take the integral with respect to t. All right, thank you for your time. Have a great day.